Okay, so in this session, we're going to do a sample tetracorder run. I have a couple of directories set up. I have a cube here. This is an imaging spectroscopy cube from AVIRIS, flown in 1995 and calibrated to apparent surface reflectance. The data are scaled 16-bit integers, where a reflectance of 1 is 20,000 dn. And this was done in the 90s to save space. Today, we use floating point data. This cube is also, the .v is Vickr format. Tetracorder reads 16-bit integers or floating point data in both Vickr and ENVI format. So you'll see in some cubes that I work with and are on PAN, and if you get AVIRIS data from the Jet Propulsion Laboratory, they have ENVI headers, and Tetracorder reads those just fine. The key, however, is that the cube must be in band interleaved by line, BIL format. No other format will work, and that's efficiently or the most efficient format for both extracting spectra and reading images in a reasonable amount of time, especially as the cubes get bigger. Efficiency drops if you're not in a BIL format. So we're going to run Tetracorder 5.26 in this example, and I have an example line, command line here to get started. So the other limitation of Tetracorder is the path to the image cube must be less than 74 characters. And that's due to the parser routine that's in the SpecPR system. So the cube here you can see is a fairly long file name. So if we had it off in some other directory buried down, the path length could be quite long, and in which case you might go over that limit. You can circumvent that limit by setting up a symbolic link on a Linux system or a Mac. This was a test run, so I'm going to remove this directory, and we'll regenerate it. So the commands is basically this with options. So what we have, let me show you there's a bunch of different Tetracorder versions here, and these are different versions that have different expert systems. And so we keep all of these separately so that if you want to reproduce a particular run, you can do that. And there's even older versions in version 4 are stored in another directory, but that needs a different compile of an earlier version of Tetracorder. Basically, if you see a Tetracorder 5.1 will not run a Tetracorder 5.2 expert system. So you need to run a Tetracorder that's compatible with an expert system. This is as we add features that need to be decoded as keywords in the expert system. The Tetracorder source code will parse those correctly. So we're going to be running 5.26e. That's the latest version. And so we are in a different directory than where the setup expert system is located. And so we need to execute this command, and if we execute it with no options, it tells us what the options needed are. So we need to have a subdirectory, some keyword for the data set. We're going to be using a cube We can also do single spectra. Then we have the cube name, the scale factor. If it's floating point, the scale factor is usually 1. In our case, it's 1 over 20,000 since they're scaled integers. If you're in single spectrum, you can follow a growing file. For example, when we were doing rover operations, when the rover was driving from one place to another, the spectra were continually being acquired and reduced and tetracorder run, and it followed the growing file, giving results as they came in real time. Then you need a temperature and a min-max temperature range and the temperature unit. The temperature unit can be in either degrees centigrade or Kelvin, and then a pressure unit. These are constraints that, for example, if we know the temperature is near 0 degrees C or above 0 degrees C, we know that CO2 ice can't be in that pixel. So it's a constraint that helps in rejecting some compounds. Most minerals, however, for the Earth, Moon, Mars, asteroids are reasonably stable and don't get rejected by these temperature ranges. Okay, so what we're going to do is we're going to execute this command line, and let me we're just going to call it mapping 1, because if you're doing experiments, you might be mapping 1, mapping 2, mapping 3, so on. It's AVIRIS. It needs to be one of the things on this list. And adding these on the list are fairly easy. To add a new instrument, you need to convolve the spectral library and set up the pointers so it finds the appropriate restart files and libraries and things. It's not too hard to set up, and we're working on tools to make that easier. Okay, then we're doing a cube, and notice from where we're located, the cube directory is here. So from where we're currently at, the cube would be at this location. And so if you did a test of seeing this file from this location, that's what you would type. But when Tetracorder runs, we're going to move into this directory, so that would not be a valid address. You'd have to put a ... in front of it. So if you're familiar with Linux and Unix file name conventions, this is up one directory, and then when we're down in this directory, we would move up to the level that the directory cube is located. Okay, then we have our scale factor, and then we have the temperatures and pressures. So we put all those in. A bunch of checks are done. A bunch of files are copied into this directory, and we'll cd to that directory. Before I start, I'm going to copy this command. And I'm going to do an ls, so you can see all the directories that have been created. So there's a note on the license. It's GNU public license, freely available. Anybody can use it and modify the code. We'll be putting the code on GitHub in the next couple of months. So there's a lot of directories here. The main directories where results are in the group directories and the case directories. And when we get into the expert system commanding, you'll see where these come from. So for AVIRIS, the two main directories where results are the group 1 micron and group 2 micron. If you're interested in the vegetation products, there's a vegetation directory. And then there are special cases for example, this is the epidote red edge, this one here is the vegetation red edge shift. This case is for a more specific mixture series of epidote calcite chlorite, which occurs commonly on the Earth in those mixtures. So we're all set. Everything is set up here. We didn't um, get any error messages when this executed. There is another parameter here that is how many CPUs to use. Tetracorder itself is single threaded, so only one CPU will be used. But post Tetracorder analysis, where all the summary products are generated, that can take longer than the Tetracorder run itself, or comparable time. And you can use multiple CPUs to shorten that. And the default is pretty sure it's 2 or 3 CPUs will be used. Okay, so we can now execute this line, and now it's going. If you see it stop, then something went wrong, and we'll work on that when a user encounters that in our sessions here. Now there are a couple of files that are being created. So the tetracorder.out file is the Tetracorder run itself, and it's printing out. You watch this number here. It's printing out every 10th line in the middle of the image the results, and you see some of these are none. But when something is found in a group, it's reporting what it found, and for that entry, it's giving what the material number is in the expert system, the fit value for that, the depth value for that, and the fit times depth. And these are weighted fits, weighted depths, and weighted fit times depth, depending on the number of spectral features being used. A note about AVIRIS data looking through the Earth's atmosphere. The 1.4 and 1.9 micron water bands are mostly opaque, so we don't pay too much attention to these values. There's a lot of residual artifacts due to, like 99 to 100% absorption in the atmosphere, so we're not getting good quality data at the surface. This stuff works much better on Mars, or if you've got laboratory data, or like a rover where you're correcting the atmospheric path pretty quickly, or a contact probe in the field. So this will only take a few minutes, so we'll let it run. It's between 600 and 700 lines, so we're already 2/3 done. Okay, so the basic Tetracorder run is complete. It's now compressing all the files to reduce disk space. Otherwise, the Tetracorder output is considerably larger than the input data cube. And many things are not found, so compression is pretty efficient on those files. So you can see it took 3 minutes and 12 seconds to do this run, and we used 98% of the CPU. That's pretty good because a lot of files were being written, several hundred files. And in fact, the number of materials mapped was 536 with 947 spectral features. So there's 536 times 3 plus a few other files. So well over 1,500 files are created during this run. So that's a lot to evaluate. So I'm going to Control C that. Now another file is being created, and that's the full of everything that's being done post Tetracorder. So we'll look at that. And with 3 CPUs, the analyses are going along pretty fast. While that's happening, we can look at a couple of files that are already complete. And there are history tells the setup that was done, and then results. If we go look at the results file, Tetracorder generates this, so it tells you, the number of features and everything that it's doing. It's telling the image cube that was done, that was analyzed. Then the groups. So group 0 is applied to most of the other groups, and notice we found a fair number of vegetation around. This is vegetation that's thick enough on the ground cover that looking for other minerals is not robust. So this pixel is only cataloged as vegetation, combination of green plus dry, photosynthetic and non-photosynthetic vegetation. There's a few melting snow plus veg pixels. This is noise, and because it's only 80 pixels, cacti tend to have broad absorption features similar to snow, where the water band is shifted. So sometimes cactus or other desert plants pick up snow. If we put in some more cacti in the expert system, this would probably go away. So the main groups, again, are group 1, which is the electronic absorptions that are mainly in the visible and near infrared, 1 to 1.2 microns or so. And you can see Fe3 plus hematite and goethite. So here's a lot of goethite mapping, goethite plus muscovite, and so on. So you can see if we go back up, the 3 columns here are the fit, the depth, and the fit times depth. That's an average, that's the number of pixels in each of those. And you notice they generally are not the same, and that's because we make thresholding a little bit different, and there's a strategy for this for detecting new spectral features like small shifts in an absorption band due to chemistry, and I can explain that later when we get into the Tetracorder commanding. So you can page through this and see if one of your favorite minerals mapped or not. So group 2 is similar. Group 2 is vibrational absorptions and combination bands in the 1 to 2.5 micron region. And you can see we did map a lot of kaolinite. There will be a lot of smectite, a lot of alunite should be up here. Not too much there. Here's some alunite, muscovite. So there's a lot of different minerals mapped in this area. Group 3 is detection of vegetation, including weak vegetation, which is weak vegetation signature, which is common in desert environments. Okay, so the Tetracorder run is complete. It took a total of 8 minutes, so that's pretty good run time. This is a pretty old laptop, circa 2013 or 14. It is an i7 laptop, but fairly old. A lot of these other groups won't show anything because these are outside the wavelength range of the AVIRIS data. And again, the 1.4 and 1.5 micron absorptions and 1.9 aren't relevant to AVIRIS looking through the atmosphere. Okay, so now there are a lot more directories created now. So we have all kinds of results. Let me bring up the file browser. Where did I have that? And we'll go into the mapping 1 directory. So let's concentrate on group 1 and group 2. So we'll look at group 1. So this is the output that Tetracorder does. There are two, you see a depth file, and then a depth.header, so that's an NV header for this depth file, fit times depth, and a fit file. Then there's also a GIF file of the fit times depth. And the GIF, of course, that one, let me find one that might show something like, how about I'm looking for, I was looking for calcite. We don't want copper carbonates. That's interesting. Well, let's just page through until we find something nice. See, there's a lot of things that are 0, so, oh, I'm in the 1 micron. That's why there was no calcite. Here we go. So here's Fe2 plus absorptions. Notice it says generic, so these are not an identification of a specific mineral, just an identification that the mineral has Fe2 plus in it. Let's go find more generic Fe2 plus bands. Okay, here's goethite. So we had to page through quite a few to see the goethite. And then if it's only a small outcrop, like here's just a few pixels, it's hard to know where that is. So, and one other note before I leave this directory, the NV files and the gzipped files, the depth, fit, and fit time depths, are linear files. They are scaled 8-bit image files. We can change the scale, the scaling in the command file to be 16-bit output, but we found that most cases we've ever done, the 8-bit scaling is just fine. Okay, so let's go down to the results, and we'll first go to the results 1 micron, and these are JPEG files. Now these files are a grayscale image with the pixels that mapped in red. And you see not much is showing here. We'll page down till we find something. So there's chlorite plus muscovite. Now, again, this is a lot to go through. Now, what it used to be before version 5 Tetracorder is we only had the NV output, and you'd have to use something like NV to view the linear files and stretch them yourself. These have all been stretched with a tone curve similar to what a digital camera produces. So it shows you both detail in the highlights and the faint stuff in the same image. Okay, so now another way to look at the problem is the duals. And let's go to the 1 micron duals. So now we have the grayscale image that we were looking at before with the red overlay, and then the GIF image is put on this side. Of course, we've changed it to JPEG, but that's different. And these are lossy, but so they're really browse products, but it allows you to browse pretty quickly. And we can go through a few more. So you can see here that the pixels are faint enough that the reds are kind of hard to see. So that's why we do the dual. So you can see that something mapped, and then you can look on the red on the grayscale image to see where. So if you're going to look for an individual mineral and its location, this is a good product to look at. All of that still takes a lot of time. So notice that there's a not 0. So all the images that actually map something are put in this directory. So those images are all here too, but a lot of images with nothing found is in here too. So this cuts the time to review things. So um, there's a couple of tiny pixels over there for this. So even if one pixel map, it'd be put in this directory. But it's quicker to go through this directory than the others. Okay, now there's yet another product, and that is the color results. And the color results with labels, again, the water absorptions don't show anything, so we'll skip those. So here's hematites, goethites, and Fe2 plus minerals and different color codings. And if you have a particular science problem that you need to emphasize certain minerals or products, that's pretty easy to do now. It's just a script that lists what files and what color you want to assign to each thing that goes onto the map. And these are also gamma stretched, so there is intensity here. So you see the orange is more intense up here, and then with the float coming down, it's a fainter signature, so the absorption band depth is decreasing. So the abundance would be highest up here. Similar over here, high abundance and lower abundance of the hematite. Clays, carbonates, and sulfates. Another, so this is 2 micron minerals, the stretching modes, whereas this is electronic transitions. And then another way with a different set to emphasize for the vibrational absorptions. Then this is one that just shows the iron oxides, the ferric iron oxides, hematite and goethite with the grain size series. Prehnite, chlorite, serpentines. This one was designed for Mars CRISM data, where we do see mixtures of chlorite, serpentines, and prehnites. And you'll notice that we do have a few scattered pixels. When you see scattered like this, it's likely noise. And in this case, what we found is that for the Earth, chlorite, serpentine, plus some dry vegetation have absorption bands that overlap and mimic the prehnite plus chlorite. So basically for Earth, you can look at all of these as chlorites or serpentines. Pyroxenes, there's a couple of pyroxenes pixels over here in these mountains, and I haven't gone to this location to see if those are real. So it's possible, but would need verification. Vegetation, let me jump ahead to the next one. This is the vegetation signature, and we see the army green kind of color. So there's trace green vegetation everywhere. Wherever there's chlorophyll, we can do the red edge shift position, even when the chlorophyll absorption is very weak, and this shows the band position. Now, there can be reasons for the band changes. It could be a species change. It could be a water change within the same species, or both, a combination. So it just gives you an indication of changing of the chlorophyll absorption. Then water, there's no water in the scene, but we commonly map the water, and you can see the various conditions that we map. And we can add more. Broad absorption bands, if you remember the results file, we mapped a lot of sphalerite. And sphalerite, we need to rename that output to be a generic, because it's not a unique identification as sphalerite. It's a curvature in the 1.5 micron region. So there's curvature in the data, and that's being picked up in these. In other locations like here, we're picking up some olivines, so which is interesting because the pyroxenes were over here also. So that adds credence to maybe we did see some pyroxenes. And pyroxenes and olivines map nicely on the moon and on Mars with this exact same expert system tetracorder run. And we're back to our beginning, I believe. Yep. Okay, so I generally look at these products first, and sometimes I just use these products. And then if I want to look at details, then I start going to the results dual. Okay, now there's several other things that have been created also in the results. There's results cluster and results cluster sorted. And and then filtered out the not zero. But let's look at this one. Actually, there's a neater command, less. If you aren't familiar with that one, it's a nice command because you can move forward and backwards. Okay, so this is a cluster analysis that is the radius of the cluster, so it gives a confidence level of is it real or not? And then by the shape of this structure and looking at a number of images, we put a qualitative um, result over here. So if everything's zero, yeah, nothing was found, so it's zero. If the clusters aren't very well behaved, it could be there's probably nothing there. But if you're really concerned about that entry, then you'd have to go look at it yourself. Let's get down to the 1 micron region. This is sorted um, um, by the groups. So here we see WOW. So we did map a lot of nanohematite, and we know that. So there's a lot of WOW and great. And so if you're looking to put together a flashy, colorful image of your results, you choose the best ones here because they'll be mapping all over the place and generally produce some nice different colors. And we can go down to the 2 micron region, and we see wows and goods and greats. So you can look at these and see whether or not something is reasonable. The budding tonight, for example, we can go look at the budding tonight, and it says great. This is just a few small pixels, and in fact, it might be good to go show that to show the sensitivity of this. It's a wrong one. Nope, that's the same one. We want this one. Let's see what. Oh yeah, feldspar. So this small grouping here, and if you see a few red pixels here, has resulted in this this entry here in the results files. So there's a lot of tools you can use for between looking for things, seeing how good things mapped, um, to try and synthesize down in your mind what you've actually found with this tetracorder run and what you want to go for in terms of further study and getting your science questions answered. There is another thing that we haven't done, and I'll set that up in another example. But for for all these minerals that are found, we have a tool that will go and extract the average spectrum for all those pixels that were mapped and put that into a specpr file so you can look at the average spectra. And I'll set that up in another session. So with that, we that finishes up this session pretty well.